Everyone. We are going to finish up our chapter 6 today. Now, the last session we stopped at, the arrangement of palms in parallel and series. There are differences in the total of discharge, the head, as well as how you compute the efficiency. The power will be the same though. The power of the total system, regardless of whether the palms are arranged in series or parallel, they are actually the summation of the power produced by palm A and palm B, or if with more than two palms, that means the summation of all the powers provided by all palms. Um, Now, if you look at this, right, let's recap what we have learned last time. Um, okay. Um, if we look at, palms arranged in parallel, right? Okay. We have palm A, palm B. Okay. This is just, two palms. It could involve more than two palms, which are arranged in parallel. Um, Now, last class we have already learned if the palms are arranged in parallel or installed in parallel, then the Q will be the summation, QA plus QB. We have looked at the head produced by both palms. They are the same because throughout the system, right, you only produce one hit, all right, unless it's in series, then it's being produced, the addition to the hit is being produced twice lah, all right, or more than that if more pumps are involved. Power, it will be the same. For either you arrange your pump in parallel or series, there will be the addition, all right. Okay, now if you look at this efficiency, right, it's basically the formula would be QT times HT, that means the total, divided by K times P total, all right? If you look at here, P total would be PA plus PB lah. All right, this is the one. Q total would be QA plus QB, this one. And then HT would be just HT lah. All right, or HA, either HA or HB lah. For the unit constant, right, you'll be using 0.120, 0.102, okay, for P in kilowatt. Okay, that means your P is in kilowatt and your Q in meter cube over second. If you are using Q in liter over minute, okay, it's just not liter over second, but liter over minute, and your P is in kilowatt, then the coefficient or unit constant would be 6,116. Okay. Now, this is pump in series. Q would be the discharge, will be the same throughout the system. Okay, Q total equals to QA equals to QB. Meanwhile, the head, right, it will be, increased twice as much, all right, which is the addition of HA plus HB. Total power produced would be the addition PA plus PB. Okay. Similarly, right, this would be QT times HT. HT is the addition. That's why if you look at it, right, and then K times P total. Okay. So this is H total, Q total times H total divided by K times P total lah. All right. That it will be the the general equation. This diagram, again, it shows lah if you plot, your head, okay, and against your rate of flow, all right, for pump in parallels and series, okay. This is in parallel, okay, your discharge would be twice as much, your head is just the same, all right, throughout. Meanwhile, if you look at this, the head increase, right? And then your rate of your discharge should be remaining the same lah, right, for the whole system. Okay, now let's look at this activity. I think I asked you to try this activity. We'll just go through the, how we are going to look at this lah, right? How we are going to solve this. I'm going to reshare the file. Okay, let's look at this exercise. You have activities 6.3. The question asks us to find find Q. You have pump A and pump B. Okay, if you look at the question, right, it says pump A and pump B are actually installed parallel to each other. So you have A and B, so they are installed parallel to each other, right? Okay, and then the head of the system is 27.4 meter. Now this head, right, if you still remember, right, if the pumps are installed parallel, okay, HT would be the same as HA would be the same as HB lah. That's why it gives you the head, the total system, the head of the system. Okay. And then the question asks us to find what is the system discharge, power, and also efficiency. Okay. Now, discharge would be, okay, you have QA, QB. Now, Q total will be the addition lah. Okay. Q total is QA plus QB, which would be, if you look at here, QA is given as 0.0473 plus 0.052. That would give us 0.0993 meter cube per second. Okay, you add them up together. How about power? Power, regardless, okay, whether a pump is installed in series or parallel, they are the addition for all the pumps, right? All the power produced by the pump, which would be PA plus PB. If you look at the table provided, that would be 15.3 plus 19.1. That is 34.4 kilowatt. Okay. Finally, the efficiency. Now, the efficiency, all right, is given as Q total, H total divided by K, and then you have P total. In this case, Q total will be QA plus QB, which is this guy here, 0.0993 times H total, which is 27.4, divided by, now since I'm using PT in kilowatt, okay, if you still remember, the constant would be 0.102 times 34.4. That will give me, can somebody help me calculate this, please?
0.775.
0.0 eh yeah, thank you, Mohammed. 0.7754, right? Okay, so I could give this in terms of, I could, rewrite this value in terms of percentage. I will write it as 77.54%. Okay, all right, that's it. It's very straightforward, eh? So let's look at the next one. I'm going to share this slide. Please remind me if I forgot to share this with you guys. All right.
Doctor. So
Last
we,
time I only reminded me. Thank you. Now let's look at activity
Doctor,
6.4.
Doctor,
Okay.
Doctor,
Let's use a new paper.
Doctor.
Okay. Activity 6.4 asks us to calculate all this. All right. Discharge, the head, total power, and then the efficiency for two pumps linked in series. So I have pump A, pump B, okay, as given in the table, right? They are linked in series, okay? So I have, for in this case, H will be the total, Q will be the same in the system, power will be the total of two pumps, okay? Of course, the efficiency would be uh, this one lah. All right. You can use the formula. Um, okay. Um, okay. You have system discharge given as 0.043 meter cube over second. Now, by now, you should know the Q remain the same, right? So Q total would be QA equals to QB, which is this guy here. And then impeller diameter. Okay, the diameter of pump A and B. Okay, this is 24.4. This is 30.5. Okay, now the question asks us to find discharge. Okay, for the system. So you have this. Okay, discharge for the system. You already got it. Then what else? You need to find the pressure head. The pressure head would be H total equals to HA plus HB. If you look at the table, it's actually given as 26.88 plus 33.5. That would be 60.3 meter. Okay. And then total power. Again, power would just, you need to add them up together, which is 15 plus 19.9, which is equal to 34.9. Okay, kilowatt. What else? Efficiency. Efficiency would be QTHT divided by KPT, which is 0.0437 times 60.3 divided by, help me check my answer, just in case I have, miscalculated. This will actually give me 0.8012, which is also 80.12%. Right? Okay. Help me check whether it's correct or not. Right?
Correct, Doctor.
Is it? Oh, somebody is joining. Sorry, I didn't. Okay. Okay, is this correct?
Correct, Doctor.
Okay, thank you, Priya. And then let's look at the next exercise. If you notice,
Betul.
right, chapter 5 and 6 are quite straightforward.
Betul.
Doctor.
Yes.
The EA
Vincent?
is efficiency or what?
I'm sorry?
The EA,
Huh?
the the table.
The table?
Got either EA.
Oh,
EA
EA
is
is the efficiency.
no need to use.
No need, no need, because it's actually telling you the efficiency of pump A and pump B. You can actually find the efficiency using this formula as well. Okay, Jinseng?
Okay.
All right. Sometimes, right, if you look at this question, right, it actually gives you a lot of, here we put E is actually the same notation as this eta here lah, all right. It also gives you a lot more information, for example, the diameter, okay, and also the speed, you not necessary you need to use all right. Okay. Um, let's look at one more activity here, which is activity 6.5. You have a pump, all right? Now, this pump, you need to supply as much as 22 meter cube over second of water. That means this is a total under a head of 18 meter. That means the total, the total system, the system, what I mean is the total discharge and head provided by system will be this value. All right. So what I'm going to write is, I said Q total is 22 meter cube over second. And then HT would be 18 meter. Okay. It says two identical pump. That means the same pump, the power, everything would be the same. Installed in series. So you have two pumps installed in series. Let's name it as pump A and pump B lah. Okay. Now in this case, you would know QA will be equal to QB will be equal to Q total, which is 22 meter cube over second. All right. That you know. And then the head. HT is HA plus HB. Okay. By now you should know, because H total is 18, right? That means you are going to divide by 2. Since they are identical pump, they would produce the same head then. So this would be, if you want to find HA and HB, that would be 9 lah, right? Since the total will be 18. So HA equals to HB equals to 9. In this case, because they are identical. Okay, since A and B are identical, right? Okay, you need to find power delivered to the flow by each pump. Each pump, that means one pump. Okay, here's the thing. What else information? You have efficiency provided, which is 0.72, and then the top would be 11 kilonewton meter. Okay, so power, let's say by each pump, right? The power would be, okay, before that, I wanted to ask you, do you still remember what is the power of a pump? The formula? Okay. If you still remember, the formula for power of water would be rho GQH. For mechanical power would be 2 pi NT over 60. Okay. Now, in this case, let me ask you, okay, here's the thing. You have input, you have output. May I know for pump, What is your input power? For pump, you are providing energy, right, to the water. So the output would be, and your input would be, am I right? Do you still remember?
Yes.
Okay, great. Okay. All right. So this will be your output power. You want to know because you are producing, right, power, right, to the water. So what we have here is you can find the power produced by each pump, which is PA equals to rho GQH. That will give you 1,000, assuming 1,000, the density of water, 9.81 times 22 times 18. So that will give you, how much? Oh, sorry. This one is 9. See? Because I'm using A, right? This would be HAQA, all right? Be careful. That's why we need to, initially, right, they asked us to find what would be our, QA, HA, or HB lah, right? And then the power for individual pump. So this would be, could help somebody help me?
One nine four two three eight.
I'm sorry?
194238.
Okay. I got 1.942 times 10 to the power of 6. What? Is it the same?
Yes, doctor.
All right. Okay, great. Thank you. Okay. Finally, you need to find the shaft power and the speed of each pump. It says each pump, eh? All right. Let's look at this. So,
Doctor,
yes.
for the I, if I directly use the H is 18 and I final step I divide by 2, can or not?
Can I?
Can I?
Because actually, yeah, this is actually division of 2, 18 divided by 2. What you mean is you want to
I
find
use,
HA, right? Can also?
So I use P out is the total of 2 pump and then I divided by 2 and get one each one.
Can also?
Okay, all right, doctor.
All right, okay. Because they are the same, right? Okay. So once you have that, but I'm not sure if you have any power here if you want to divide by 2. Again, you need to find a single power, right? Because power is not provided, right? All right. Okay. And then after that, you need to find the shaft power. Now you know that shaft power is the mechanical power. All right. The efficiency would be 72%. Here's the thing. There are 2 ways to find it. Let's look at this. Okay. Not 2 ways lah. There are actually 2 steps lah to find this. Okay. The total power of the system, right? Okay, would be QTHT divided by K T. All right. So in this case, your Q would be 22 times 18, okay, which is HT, divided by 0.102 times your efficiency provided would be 0.72. Okay. So the whole system would be, okay, which is 5,392.2 kilowatt. Okay. Now you have this, all right? So P system, the total would be PA plus PB, that you know, which is actually this guy here. Okay, so the single power would be 5392.2 divided by 2. This will give you 2696.1 kilowatt. So you are trying to find your torque, all right? Sorry, your speed, because torque is provided, which is 11 kilonewton per meter. So the speed is, you are going to rearrange this formula. You are going to have which is this would be 11. What is, okay, here's the thing. I actually have, this supposed to be times 10 to the power of minus 3. This also supposed to be times 10 to the power of minus 3. I could cancel them. Alright, since this is in kilowatt and this is in kilonewton meter. But however, you can have them. This is 3.142 lah, right? So the speed would be, if you can help me calculate this should be 2340.5 revolution per minute lah. Okay. Okay. Any question on this question here, activity? No question?
No.
All right, thank you. All right. Okay, final topic that we are going to look at. Not final, I think there is another topic which is a 6.8. So this is the second last topic that we are going to look at, which is a similitude for pump and turbine. I think you have already learned about similarity analysis in your fluid mechanics. You know, where you have done similarity for geometric, kinematic, and dynamic. If you still remember, right, when you analysis the similarity for geometric, it only involves length scale. That means it could be, you know, you are analyzing diameter, the distance, all in length scale lah. That means in meter, centimeter, in inches, right? The dimension is L. For the purpose of kinematic similarity, normally it involves LT. That means the dimension of length and also time. It could only involve time scale. All right, that is kinematic. It has something to do with time lah. All right, that means it's velocity. It could be acceleration. All those lah. Okay, which involve length and time. It could be frequency as well. Okay, which involve only time. And then dynamic similarity, if you still remember dynamic similarity, normally you have M and T. That means actually MLT lah, all right? MLT or FLT. F is the force. But the dimension that are involved in dynamic similarity would be the mass and also length and time. Sometimes it only involves mass and time. All right, as long as it has mass and time, that means it's dynamic similarity already. Okay, but typically you have MLT lah, right? Okay. Let's look at the scale ratio. Sometimes we wanted to study about ships. We would build a smaller size model to study about the buoyancy and things like that. I think you have done it maybe in your fluid mechanics laboratory where you study buoyancy. Okay, you assume where you put the ship, all right, in a bucket of water. Okay, so you try to find the center of gravity for that ship. All right, so you have model. Prototype is actually built in actual size. Okay, so it's in actuality lah. So you would assume that the prototype is actually the is a realistic, right, or the real object, okay, or structure. Why we build, we have this similarity analysis. Of course, it save cost, it save time, labor, and then in terms of you want to predict the performance of object or structure lah. You don't have, to test you don't have to build a huge or in real dimension ships just to test it. So you can build a smaller size. Now we are in subsequent slides, right? We are going to look at how we are going to analyze, okay, the model with respect to the prototype that it should be lah, all right? If you look at this, right, on the left diagram, right, that would be the model of a Pelton blades or wheel. Okay, on the right hand side, it will be the prototype, which is more to the actual size lah. All right, so it's it's how many times bigger. Okay, so you save in terms of material, you already save when you build a model, right? And you can use a model for teaching and stuff as well. This is a turbine. This is a real turbine, which is actually a turbine that use, a series of turbine which are used to generate hydroelectricity at Hoover Dam. So if you look at there are a couple of people, right, standing next to it. So if you look at the size of the turbine, it's huge. Of course, the size of the turbine depends on the capacity, how much you want to produce, how much you need, and things like that. Okay, so we are going to look at how we are going to analyze similarity. Let's look at this. All right. All right. Before that. Okay. If you look at similarity, right, in pump, okay, basic repeating variables are, if you look at all three laws, which is the similitude law for head, similitude law for discharge and power, the repeating variables will be N and D. That means in all three laws, you have N and D, right, which is the speed, rotational speed, as well as the diameter of the shaft or pump lah. All right. Now, for similitude law for head, if you look at here, you have the head. For law of discharge, you have discharge, and for power, you have power. Okay. So this is how you are going to apply this law between model and prototype. Subscript M stands for model. Subscript P stands for prototype. You could Well, this is just, you know, a notation. If you are comparing between two, right, that means model A and model B, maybe, or prototype at A and B, you could use subscript of A and B. It doesn't matter, all right? This is just an example where I'm comparing between model and also a prototype. Specific speed, which is dimensionless, no unit, is given as n times square root of q divided by h to the power of 3 over 4. Okay, so n would be in revolution per minute and so on lah. All right. Two homologous palm would have the same specific speed. You can check. You can check for specific speed of palm A, and if palm B is homologous to palm A, then you are going to have the same value of ns as well. All right. So this is just comparing model and prototype. All right. If they are homologous, then they are the same. Okay, let's look at one activity because I actually don't want to show too much about the simulated law because I'm going in for your activity. It's easier to show how it works. Okay, now let's look at this. Okay, activity 6.6. So I'm going to reduce this. Okay. We are going to have activity 6.6. Okay, it says pump A and pump B are homologous. They are operating at speed of 600 revolution per minute. Okay, so this is speed, not specific speed. So I have A and B. Okay, now to analyze this, right, if you are using simulated law, right, it's easier if you build a table. Okay, or you tabulate all the data. So I'm going to have A, B. Okay, so I have pump A and pump B. Let's look at what are the given variables. A and B are operating, so I have the speed. Okay, what else? Pump A has impeller with diameter 500 centimeter, and then discharge 0.4, head of 50. Determine size of pump B, net head, and specific speed if the discharge is 0.3. So I have discharge as well. So QA is 0.4. It doesn't matter how you arrange it. You could just write, the diameter first or head first. All right. I could also write Q first. It doesn't matter. All right. Then what else are given? Diameter of A, which is 0.5 meter. I straight away change. I hope you know how to, from centimeter change it to meter. All right. It's 100. The scale of 100. And then what else? The head, which is 50 meter. This is not available. Okay, here. Now, you are asked to find dB and you are asked to find HB as well as NS, which is specific speed. It doesn't matter, all right? You want to find NSA or NSB, you can check later. But if you don't have time, you just find one. I would suggest you to find NSA. Why? Because if let's say if there's something wrong in your calculation here, at least when you try to find NSA, you have less probability to get this wrong, okay? Since these are all given. All right. Now, let's look at our simulated law. I have law for head, which is CH equal to H over N squared D squared. I have law for, law for discharge, which is Q N D cubic power. And I have law for power, which is, okay. Now, let me ask you a question. Between all these three laws, if I want to find my dB, which law should I use? Because of course I need to look at what are provided. Can I use this? I cannot. Can I use this? Yes, I could use this if I want to find D, because H for both, H for both are not available.
Use CQ.
Huh?
Use CQ.
Okay, use this. Thank you. All right. You are using this because if you look at this, Q for pump A and pump B are available, N as well. So the only unknown would be dB. So we are using this. So how I'm going to write it is Q over N D cubic power. So this would be A, B, B, B. So I'm comparing between pump A and pump B. So I need to find dB. So I'm going to rearrange this. I said dB cubic power. If you want to write the whole thing in power of 1/3 also can. So I'm going step by step. So I'm going to rearrange this. QB divided by QA. And then I have NA divided by NB. What else? dA to the cubic power. So I have that. So dB cubic power is, my QB is 0.3 divided by 0.4. NA and B, you can write 600 divided by 600. It doesn't matter. I could also write 1. Okay, since both are the same. Okay. So this will actually give me 1 lah. Doesn't matter. Okay. And then dA to the cubic power, which is 0.5 cubic power. So dB cubic power is, what is the value? If you can help me check, I got 0.09375. Am I right?
Yes.
Okay, thank you. So dB would, since I want to, make this 1, I need to times 1 to the power of 3. This one, 1 over 3 as well. So this would be, give me
0.4543.
Okay, thank you. This will be in meter. So if I want to state it in centimeter, that would give me centimeter, 45.43 centimeter. Doesn't matter because I just want to make, well, you can write meter, it doesn't matter. All right. Because the question initially give me centimeter, right? So both are right. I'll give you full mark as well, even if you say in meter only. So that is for the diameter. Okay, so I'm going to put it here, which is 0.4543. Oh, sorry, meter. Okay. The next one is you want to determine HB. So I guess, just now, okay, you have been using this. The only laws that relate H would be the simulated law for head. Am I right? So you have to use this, okay? So H, you don't have to compare, look at the others already, okay? Now, my goal is to find HB. So I'm going to rewrite this and make HB becomes the title of the equation. The subject lah. Okay. So I'm going to have this one, it doesn't matter. This one, it doesn't matter. You can write it, as one, the whole thing. It doesn't matter. So what is, that means you're actually calculating, this times 50. So I think you are going, how come it's darker? Okay. Did you get 41.28 meter?
Yeah.
Okay, great. Thank you. Not sure whether you got it or not. Okay, now, finally, you need to find the specific speed, okay? Specific speed, if you still remember the formula, right? Okay, let's find specific speed for pump A first. The formula would be N square root Q divided by H to the power of 3 over 4. Which would be, I'm using NA lah. NA, QA, HA. So NA would be 600, QA 0.4, HA 50 to the power of 3 over 4. Okay, so that will give me 20.18, is it?
20.8.
No unit, Okay, you can check for NB. What I mean is, you are using the same, you change it, QB, NB, QB, and HB. You are going to get the same as well, all right? Okay, because they are homologous, Okay. So far, any question? It's kind of straightforward, I don't think so. You have question lah on this. Okay. Okay. This one, I want you to try this out yourself. If you have problem, let me know. Okay. But I'm going to provide you the answers lah. Okay. It's straightforward as well. Okay. Let's look at performance of turbine under unit quantity. Here's the thing. If the question asks about, the relating to, ask you to find some quantities under a unit net head, right? You are going to use this formula. Notice that, okay, if you look at this formula, right, compared to the simulated law of head discharge and power, right, they have repeating variables of N and D. In this case, right, if you are looking for unit discharge of Q, it's Q over a unit of head. All right, it doesn't matter to the power of whatever lah, right? This is H to the power of half, right? And then if unit speed is N over H, if unit power is P over H. All right. So I hope you can distinguish between the simulated law and also unit of these quantities. Okay. this is just, you know, you are comparing between two similar pump or turbines. It's just either A, B, or 1, 2 lah. It doesn't matter. All right. This is how you write it. It's the same concept as you are solving for simulated laws of simulated. Okay. Let's look at one activity here. You have a Francis turbine, which produce 6,750 kilowatt of power at 300 revolution per minute. Just a second, I think I forgot something. Okay. You know, initially just now we look at similarity in pump, right? This is similarity in turbine. If you look at it, it's the same. You have repeating variables of ND as well. Okay. It's the same. Almost similar in both cases, right? Okay. The same, you know, the same concept to solve it. Let's go back to this activity here. You have Francis turbine, which produce power of 6,750 kilowatt. This is N, the speed. This is your power. Under net head, it tells you a net head of 45 meter with overall efficiency of 85%. Determine N. That means the question asks you to find N, Q, and brake power of the same turbine under a net head of 60 meter. Okay, in homologous condition. So you need to find, you know, the speed, the discharge, and also brake power under a unit net head. So this is how you are going to do it. You are comparing both turbine 1 and 2. Okay. The first thing you need to find would be the speed. Okay, for turbine 2. So you are comparing for turbine 1 and 2. So this is just, if you look at, you know, since you want to find the speed, you are comparing both. It's quite straightforward lah. You substitute, you know, substitute the head for turbine 1 and turbine 2. This is just rearranging, right? You are going to get your speed lah. Okay, for turbine 2. Similarly, if you want to find the discharge, right, you are using the same formula, except that, I guess in this case, right, you are not provided discharge for turbine 1. Therefore, because power is provided, therefore you need to get, you know, your discharge for turbine 1, where, you know, this is provided. In the case of turbine, okay, P in would be the water, P out would be the mechanical lah, right? I hope you still remember. So that's why I make sure. I actually, the other day, I wanted you to know how to distinguish between, you know, the operational of pump and also turbine, right? What is the input power and output power? So it's quite straightforward. You are using the unit quantities for Q and also the power lah. So you are going to get it straight lah after, you know, you substitute all the known values. Okay. So this is how you do it lah. I think that's all for, you know, our chapter 6. Do you have any question so far? Try to
No, doctor.
Okay, no. Okay. All right. If no, can we take a group photo, please? Could you switch on your camera for a while? Just
Can.
Can okay. Anyone else want to switch on your camera? Okay, no more. Okay, I'm going to take the photo on the count of 3. I think some of you, I have a couple who are not able to join. I think not able to switch on your camera. Okay, on the count of 3. Smile, everyone, or cheese. 1, 2, 3. One more, Okay, one more freestyle. Okay, 1, 2, 3. Okay. Right, thank you guys. Now next week, Sunday and Wednesday, I'm going to go through your hydraulics lesson to prepare you for your final exam. All right? Now I know who are you already. Okay. Take care guys. I'll see you next Sunday then. All right?
Thank you, doctor.
Thank you, doctor.
Thank you,
Thank you,
doctor.
doctor.
You're
Thank you,
welcome.
doctor.
Thank you, doctor.
Right.
Thank you, doctor.
Thank you, doctor.
Thank you,
Thank you,
doctor.
doctor.
Thank you, doctor.
Thank you, doctor.
Thank you, doctor.
Bye.
Thank you, doctor.
Doctor, can you share again the
Thank you,
attendance
doctor.
I'm sorry?
attendance link? Can you share
Oh,
again?
okay. All right.
Thank you, doctor.
Thank you.
Thank you, doctor.
Thank you. All right, already shared the attendance
All
link.
right.
Okay.
Thank you,
Thank
doctor.
you.
Doctor, the assignment 6 can start already, right?
Yeah, can already
Okay,
submit. Which would end next week lah. All right, submission
Okay.
date. All right.
Okay.
All right.
Thank you, doctor.
Bye.
Bye-bye.
Thank you.
Thank you, doctor.
Bye.
Thank you, doctor.